Okay, students, let's try this one more time. I forgot to turn my microphone on. So, what I'm going to do is I'm going to walk you through what I've already completed. I just caught it right before I got to the end of problem 10. All right, so let's walk through the problem. Number 8, chapter 10, page 356. Excuse me, chapter 11. Two people are carrying a uniform wooden board that is 3 meters long and weighs 160 newtons. If one person applies an upward force equal to 60 at one end, at what point does the other person lift? Begin with a free body diagram. Okay, so we draw a free body diagram, as you can see here. All right, you can see our free body diagram. Notice you've got force 1 is up, force 2 is up, because it says at which point does the other person begin to lift. Well, we know that the center of mass of the board has to be right in the middle, and that midpoint would be what? Well, it'd be 1.5 meters, wouldn't it? Which is also the center of gravity, since we are all on the same level. Okay, we're all at the same altitude here, so we can say center of mass is center of gravity. So this becomes a sum of all forces problem, doesn't it? Yes, it sure does, because look, first of all, they are using forces to lift the board. There's no acceleration because the board is not accelerating. Doesn't tell us it's accelerating. So all it was is, in other words, at what point does the person begin to lift in other words, to balance the force, okay? So that means the sum of all forces is equal to 0. So we write our sum of all forces, F of 1 plus F of 2. Now you can it doesn't matter where you put the F1, F2. Minus the weight of the board, because weight is down, they're picking up, so both of those have to be positive. Weight is down, so that's equal to 0. So solve for F2, so F2 is equal to the weight minus F1. So we just plug in our values. 160 minus 60 is equal to 100 newtons. Now you say, well, I thought we had to find the point. Well, before you find the point, you got to find the force of F2, because then it becomes a dynamic equilibrium problem where the sum of all torques is equal to 0, okay? And you said, well, how do you know? Well, because the force applied here, the force applied here, they cancel each other out. So the sum of all torques is equal to 0. So now it becomes a torque problem. So we have the torque of the F of x of 2 minus the weight of the board. Okay, weight times x is torque, is equal to 0, so solve for x2. And you plug in your weight, which is 160, your F2 we determined or calculated, which is 100, times the center of gravity of the board, center of mass, center of gravity, which is 1.5 meters. And you get an answer of 2.4 meters. So that is the point at which the other person would begin to lift, okay? That is the point, 2.4 meters, okay? All right, so they would actually start lifting it at what? Not all the way out at the end, but somewhere right in here, okay? All right, so that is problem 8. Now let's go to problem 10. Now problem 10, boy, I tell you what, there we go, is pretty involved, okay? So first thing, let's read it. We got a 60 centimeter uniform 50 Newton shelf is supported horizontally by 2 vertical wires attached to the sloping ceiling. They give you the figure there, E11.10. A very small 25 Newton tool is placed on the shelf midway between the points where the wires are attached to it. Find the tension in each wire. Begin by making a free body diagram of the shelf. So we drew our first free body diagram. This was 75 centimeters long, or 0.75 meters, 25 centimeters or 0.25 meters. We know that from where the 75 centimeter wire attaches from here to the end of the board, it is 20 centimeters or 0.2 meters. The board is 60 centimeters long or 0.6 meters. So that means that the center of gravity of the board would have to be, which is the weight of the board, would have to be in the middle of that 0.6 meters, which is 0.3 meters, right? And then the tool is halfway in between there. So let's go over here to our other diagram and let's draw it a little bit bigger where we can see. All right, here's T2, here's T1. Here's the distance from the end of the board, 0.2. All right, now remember the entire length of the board is 60 centimeters or 0.6 meters, like I got over here. So where is the center of gravity of the board, or the weight of the board? Where is that going to center? Well, if this is 60, then it's going to center at 30. And if this is 0.2, then that means this distance from here to here has to be 0.1, okay? Now, and then of course we have the weight and everything. Now it says the tool is centered in between the two wires. Well, okay. If you take 0.2 from 0.6, the full length of the board, this distance right here is what? Well, this distance right here is 0.4 meters. All right, and if the tool is in the center, then that means it's at what? 0.2 meters. See, like I have drawn here. Here's the weight of the tool. There's the tool. Then if this is 0.4 and it's in the center, then it centers at 0.2. Well, if that is 0.2, then what is this distance? Well, we already know this distance is 0.1, then that distance also has to be 0.1, okay? Now let's look at our equations. You say, what kind of problem is this? Well, we're looking at torque. We're given forces and we're given distances, or X, or R, whatever you want to call it. Look, y'all, X, R, L, same thing, all right? Lowercase l, not capital L. Capital L is angular momentum. So we are at dynamic equilibrium. You say, how do you know that? Because it's not moving, okay? It's not rotating one way or the other. So we are at dynamic equilibrium, so the sum of all our torques would equal 0. All right, now what we're going to do, you have to pick one to start with, okay? In other words, you got to pick one of the cables to start with to determine the tension of the other. Whichever one you pick to start with, which in this case, I started with T1. In other words, I started right here. Well, now look, guys, if we're counting this as our point of reference to T2, well, look, there's no torque here, okay? There's no torque. All the torque is out this way. You follow me? Because this is my point of rotation. This is acting like my axis. Well, what about T1? We'll get to it in a minute, okay? We got to find T2 first. So we're going to let this be 0 so we can find T2. So we say 0 minus the weight of the tool. You say, why'd you go minus? Because it's going down. The tensions are going up, okay? The weights are going down. The weight of the board, the weight of the tool is going down. So it's minus weight of the tool times X of the tool. Well, X of the tool with relation to what? Well, the weight of the tool is, it's in relation to where it's centered from here to there, all right? So the weight of the tool minus the weight of the shelf times, and that's not supposed to be a minus X. That's supposed to be an X. My bad. All right. That's supposed to be X. There we go. Plus T2 X of T2. Okay, and you say, why plus? Because T2 is going up, tension's going up. So solve for T2. Well, when we solve for T2, we have to add these two terms right here to both sides. All right, and then divide by X of T2, and there we get our equation. Then we start plugging in 25 newtons times 0.2 meters plus 50 newtons times 0.3 meters. Now look, again, why is it 0.2? Because we choose this as our point of rotation. Well, how far is it out to the point of rotation? Well, it's 0.2 meters. That's where the weight's applied. So, and it's at a 90-degree angle. So we don't have to do sine or anything. So 25 times 0.2 plus, when we look at the weight of the shelf, well, from here to here, y'all, point of rotation's here, all the way out to here where it's centered, 90-degree angle. You've got 0.2 plus 0.1 is 0.3 meters. Okay, and then you have to look at X of T2. Well, how far is it from the point of rotation all the way to T2? Well, you got 0.2 plus 0.1 plus 0.1, which is 0.4. So we get a final answer then of what? We get a final answer of, make sure I get it right, 50 newtons. Final answer, that's T2 now. T2 is equal to 50 newtons, okay? All right, now let's look at how we find the tension in T1, all right? Now watch very closely. Now remember, that's a force, right? So we can do what? We can do the sum of all forces, can't we? And by the way, the sum of all forces is equal to 0. So now let's do sum of all forces. Well, the sum of all forces, you say, well, now why are you going from torque to forces? Y'all, I didn't have the force of T2, so I had to use torque to find it. okay? I didn't have it. So I had to use torque. This is a dynamic equilibrium problem, okay? And both cases are satisfied. The sum of all forces is equal to 0. The sum of all torques are equal to 0. Okay, now watch. So now we can just use sum of all forces. Well, let's write our equation. We got T1 plus T2, T2, minus the weight of the tool, minus the weight of the shelf. Now here again, y'all, why minus and why plus? Tension is up, weight of the tool is down, weight of the shelf is down. See, that's why you got to draw that free body diagram. See my arrows here? Okay, see, they're up and they're up, okay? All right. So you got to keep everything right, which is equal to what? 0. All right, because we're at equilibrium. So then T1, solve for T1. So T1 is equal to what? The T1 would be equal to, I'm going to do these first. I'm going to do my positives first. You got to add both of these to both sides and subtract T2 from both sides. So you get weight of the tool plus weight of the shelf minus T2. Okay? Right? Okay. Yes, Mr. Shields, that's exactly correct. Okay, so what do we get? We get T1 is equal to the weight of the tool, which was 25 newtons, plus the weight of the shelf, which is 50 newtons, minus, we found T2, which was 50 newtons. And so T1 is equal to 25 newtons. Okay? There you go. All right. Okay, folks, I hope that helps.